Good day, folks. This is tutorial number 28, where I'm going to be discussing the precession of a spinning wheel or a top using the dynamic scenario modeling of the CATIA 3D Experience platform. Generally speaking, when I make these tutorials, I do something that essentially works. But here, I'm going to show you the issues that I ran into when I tried to do this problem. Now, a top is basically something that can be modeled with a very simple disk mounted on a massless rod, as you see here. So as the disk spins, as you basically make the top spin, this will start to move around the vertical axis, which is called the precessional motion. Okay. Now, the problem, I'm going to do a problem which the analytical solution is known, and this is coming out of Hipler's uh, basic or elementary dynamics textbook. And we are assuming there's no friction, so there's some information is given here. So the weight of this disc is 8 pounds, and the rod is assumed to be massless to make our job easier. And the top or the disc is spinning at 300 radians per second. What we like to do is to find the precession frequency. In other words, the frequency along which this top is turning around the vertical axis for two cases, 40 degrees orientation and a 90-degree orientation. The 90-degree orientation is what probably I've seen videos of where there's somebody spinning a wheel and attached it to a rope hanging from the ceiling. So we 40 degrees and 90 degrees are essentially the same problem, except that the one that's 90 degrees, people call it spinning wheel. Now, a couple of things here, and that is the dimensions of these things are given. And let's move on. Uh, the case of theta equal to 40 degrees, as I said, these are solved in Hibler's book. So basically, it involves an equation. This is the top equation, TOP equation. And in here, the moment, the free body diagram is shown next on the next page. But anyway, the moment is given by the weight of this times the moment arm about the x-axis. And this I is the mass moment of inertia of the disk about the pivot point, and of course about the x-axis, actually about the x-axis. Use parallel axis theorem, and this Iz is just the mass moment of inertia of a disk of radius 0.3. So the stuff is given here. This I is there, mass moment of inertia of the disk about the x-axis. This is about the spinning axis. And we know here this is a case of 40 degrees. In this expression that you see up there, theta is going to be 40. And in the case of 90 degrees, theta is going to be 90, which simplifies this quite a bit. If you do the 40-degree one, you basically get a quadratic equation in terms of the precession frequency, and there are two values that you're going to get. This is not the problem that we're going to be doing. Incidentally, here's the diagram, that free body diagram that goes with the previous case. I am going to be doing theta equal to 90 degrees. Now, in the case of 90 degrees, uh, actually that equation, that ugly equation simplifies quite a bit. So the moment stays the same, except that moment arm is just this length times the weight, instead of sine of 45 degrees, sine of 90, which is essentially 1. And all that ugly first terms are going to drop out. And the mass moment inertia of the disk about this axis is right there. And there's omega s, spinning frequency, which we're told it is 300 rad per second. Omega p is unknown. In this equation, the only unknown is omega p. Okay, and you solve it, you get 1.19 rad per second. Incidentally, you can find the frequency of the precession. If you find the frequency in hertz and flip it, you're going to get the period of it. Okay, now it's going to be around 5 seconds. If you go by this, it's going to be around five seconds. Now, I will show you that first of all, the one if you use disintegrator, you get something that looks reasonable, but the numbers are all off. As a matter of fact, if you use symplectic oiler, you get pretty much nonsense. Okay. Now, even with the DASSL, the the path of that point, which is the precession path, is not a circle. This is supposed to be a circle, but you're going to get something like that, and you don't want to see. I mean, I suggest you try it yourself with a symplectic oiler, and you see that you get really messy stuff that just doesn't make sense. Now, even the case that this looks reasonable, the period is completely off. Okay. Now for references, I have three parts here. There's a pivot that's fixed the ground. I gave some dimensions here, but it really doesn't matter. I'll stick to these though. But this doesn't matter because it is not moving. Essentially, it's going to be fixed. So, but we need some things associated with it, including mass. You have to associate mass with it, but it doesn't matter because it doesn't go anywhere. And this is the rod here, the dimension. I made the dimension of the rod instead of 0.5, 0.475, because this thickness is 0.025 added to that will give you from the end of the rod all the way to the middle of this, or the centroid of this disk is going to be 0.5 that we want. And the mass of it, I'm going to assign it to be 1 e to the minus 6, approximately 0. You can assign mass 0 because it won't run. It's a dynamic scenario. And here is the information about the disk. The disk, I'm going to assign a mass of 0.248, which is actually coming from 8 pounds divided by 32.2, which is 0.248. That's this number. Okay. We're going to make a spherical joint, a ball socket joint between a point here and a point there, and then a revolute joint between the disc and the rod. Okay, let's go ahead and do that. I may have to go back to these dimensions here, just this last one in particular. I'll leave it there. So we go to 3D experience. We start with a assembly design. There's three parts we have to assemble. Let me call this thing properties. I'll call it tutorial 28. Tutorial 28. I'll call it the top or the wheel actually. So a copy. Where is it? Oh, that's the name of the assembly. Right click, insert 3D part. Let's do the uh, the pivot first. So right click properties. I'm going to call this thing pivot ground. Pivot. I'll call it ground. How about that? Ground. Ground. Pivot. Okay, let's do a copy paste. Copy paste here. All right, now we're going to make it. So double click. Because I don't want to do assembly, a lot of assembly constraints. So on the horizontal plane, I will sketch. Okay, a circle that is radius 0.005. 0.005. So I'm going to draw a circle here. Dimension it. 0.005. I have already changed all my units. Oops. Sorry, this is the cancel that. Did I do here? I want the radius 0.005 feet. Okay, fine. So there we are, right there. Let me move this thing a little bit closer here so we can see what's going on. There. So there is the thing that we wanted to draw, exit, and then we pad it downward by 0.07 feet. 0.07 feet. So we're going to pad this thing, pad this in the other direction. by 0.07 feet. Yeah, there is that piece. Okay, good. And let me create a point up there, create a point at the center of a circle, because later on we want to use it to make our ball socket joint or spherical joint. So center of a circle, so there's a circle, a point has been made right up there, you can see. Now we go all the way to the top, insert the next piece, which is going to be the rod, insert 3D part, properties, we're going to call this thing rod, and rod. All right, let's go ahead and make it. It's just another cylinder. So double click on it. On that vertical plane, I will sketch another circle. Now, let me see what I wanted to do. The radius of this circle is 0.0125. So let's dimension this thing. Diameter, radius is 0.0125. Diameter is 0.05, right? Diameter, yeah. Exit. And then we're going to pad it. And the length is 0.475. 0.475. I noticed that that's this circle, and there we are. Okay, there we are. I just noticed that. I'm sorry. This was not corrected. It was the diameter, which was. Let me see for a second. The radius is 0.0125. That's a mistake. Let's go here. 0.0125. 0.0125, because it didn't look like the right size compared to the pivot. There we are. So this is the rod. Let's make sure that the length of it is okay. 0.475. That is correct. While I'm at it, let me change the color here. Properties, graphics. I'm going to change this thing to, I guess, orange, just so that it looks nicer. Now, while we're at it, let's go and create a point, because later on we want to create a spherical joint here. Let's go and create a point while we are in this rod, and again, the center of a circle. And here's the circle. The point has been created. Okay, the 2 points on top of each other, as you can see. All right, let's go ahead and make the disc. So all the way to the top, right click, insert, 3D part. Let me call this thing the disc property. Now these are very simple parts. Now I didn't have to make them here for you, but since some people want to do everything from scratch, I decided to spend maybe 4 or 5 minutes to do this. Disc, fine. Let's go make it. So on that face, on this face, I will sketch a circle of radius 0.3. That's the big disc. Let me make a dimension here. Diameter 0.6 or radius 0.3. 0.6. Oops. Yep. Okay. Exit and pad it by let me see, by 0.05 feet. Okay. There we are. And we're going to make a point here, because later on I want to plot the velocity and stuff like that. So I'm going to make a center of a circle. Again, this circle, the point is made, and I'm going to change the color here to yellow, just for aesthetic reasons. Good. So we're pretty much done with our model. Okay. Now, what I'm going to do is create my joints, spherical here and cylindrical there. So let's go ahead and do that. Let me see. We go back to all the way to the assembly. First of all, let me do a quick save. All right. Okay, so let's go ahead to assembly engineering connection. Assembly constraints fix. I'm going to fix the ground. Notice that the ground has been fixed right there. Okay, and then we're going to create a spherical joint. The method that template we're going to use is point and point. So let me do it. It's easier to select it from the tree. So from the ground, there is a point here. We're going to select it. And for the rod, there is a point. So a spherical joint is going to be created there. And say yes. So we have a spherical joint. Now we're going to do a revolute. So revolute, what is this? Revolute. Okay. I'm going to use, oops. I'm going to use the this one, uh, line, for axis, plane, and then for controlling the angle, also plane. Click on it. So let's do this axis and the axis of the disc. Let's do the back plane of the disc, and you go from the front. You select the end of the rod, and for the angle, I'm going to select, for example, let's see now, the disc and the rod. Say the vertical, the YZ plane. See the YZ plane of the rod. There we are, and the YZ plane of the disc. So that angle right now is 0, but that's going to be determining the command. Say OK and say no. Good. So we are pretty much done as far as our model is concerned. Now we're going to go to mechanical systems design. First thing I'm going to do is actually assign masses and weights to these parts. So how we do that, we go all the way to the right down here, weight definition. Notice that everything is red right now. So as far as let's start with the disk. Here's the disk. Click on this hyperlink to declare. Now right now everything is 0. So what I'm going to do, I'm going to use the properties of steel here. You click this box. Properties of steel are going to be used, but I'm going to change that thing to be 0.248, right? 0.248. Okay, good. Close that. Now we select the rod. Again, click on the hyperlink to specify the mass. Apply steel properties, but then we're going to change that thing. I said I'm going to change it to 1 e to the minus 6. 1 e to the minus 6. Okay? Basically a massless rod. Close that. And as far as the ground is concerned, just apply anything you want. I don't know what I did here. I said whatever. Yeah, whatever. So just apply properties of steel to it. You don't have to change it because that's not going to be moving. And there we are. And so we have assigned inertial properties to all of these. We can close that. Let's do a quick save here. All right. Now we're going to go and create our mechanism. You click on the mechanism. This is the name of it, or just leave it the way it is. And if you check mechanism manager, you see that there's a spherical joint, there's a revolute joint, and a fixed part. That's all we want. Say OK. Good. All right. That takes care of this. Nothing else to do here. So now we're going to go to mechanical systems experience. We already have a mechanism. We don't want to define it again. There we are. You can see the mechanism was already there. And there's a command, by the way, that angle-driven command here. Remember, I use plane and plane. Okay, so let's go ahead now. First of all, let's apply a position probe. So this point, you're going to monitor or plot the velocity of that point later on. Good. Make sure you apply gravity excitation. Click on it. and minus 32.2. The default is 32.185, whatever, or 31.185. I changed that to 32.2. So gravity is active now in the z direction, negative z direction. And now we're going to put a motor where the revolute joint is. So let's go to the velocity motor excitation. There, velocity motor excitation. Just wait for the dialog box to show up. Notice that it's expecting you to select the support. That's going to be that command. Remember, I made it plane and plane, the angle between the two. I need it because right now it's going to be asking for it. And when you do that, this dialog box opens up and says, okay, what is the angular speed of that motor? So 300 rad per second. That's the motor that's spinning. Or that's this disc basically spinning. Good. So we have our excitation, the gravity excitation, and a velocity motor excitation. Okay. So now I'm going to go create my dynamic scenario. I think we took care of everything. Yeah, dynamic scenario. Make sure that gravity is included. Make sure the motor is included. Go to the probe. Make sure the probe that you created at that location is included. And now we go to what we have here. Let's try a few things. First of all, notice that what I did is here, I said, okay, let's go 25 second, result time every 1 second, and the method is DASSL, which is fine. So 25 and 1. So that's going to be 25 and every 1 second, because the smaller this thing is, the more points you're going to get. I'll show you in a minute and say, okay, it was DASSL. That's the default, yeah, right there. You can see that right there, okay? And then just go ahead and run it. Good, done. So let's look at the trace of this point first of all. The trace of this point, there is a geometric trace here. You click on it, you select that point and say, okay, there's 26 points there. And if you want, you can say, you can go here, copy this, go back to kinematics, go to the assembly, and paste it there. Right click paste. And notice that a shape has been created, 3D shape has been created here, which actually is holding this. Now I want to show you what happens with that results thingy. Well, before we do that, let's go ahead and actually uh, plot some stuff. So we go back to the results. Okay, click on view scenario results, deselect everything. Let us, for example, plot a couple of things. Let's do x linear velocity. There's a reason I want to do that. Okay, so that's not what I want. So angular. Let's do a couple of other things. Linear velocity, x angular velocity, angular velocity. Let's check a few things. The point is that if you look at this, it looks like the period is this 25 is nowhere close to what I have. It did actually trace almost a circle, not quite, but the period is completely wrong. Okay? But it is doing what it's supposed to. You can see that. Okay, so let's play it. You see, it is what it's supposed to. That's what a spinning wheel hanging from the ceiling of a bicycle wheel should do, and it is doing that. Under the gravity, it doesn't fall, it just goes around because that disc is spinning. But the number is wrong. The period is wrong. Now, the other thing is that if you double click on this, if you double click on that, and you go and choose, say, okay, don't give me every 1 second, give me every point 0.01 second, and then run it. Just give it time. Eventually, it will go on that path as it's supposed to. It's going around with all the stuff that's happening. This is not, I mean, qualitatively, it's correct. It's doing what it's supposed to. But, you know, it's supposed to go in a circle, complete circle. There's a notation here. And I could not get this thing to do what we wanted. Okay, now I'll leave this thing the way it is. Just give it a minute. And then I'm going to change the integrator, show you what happens when you change the integrator. Okay, this is the path. This is the path of that point. These are points and they're connected together with the splines. If you don't want to see the spline, you just go ahead. We put it in this shape right here. Go down there, scroll down and hide you don't want to see that, hide the spline. So it's these points. See that? Now, let's go ahead and change our integrator. Integrator, go from DASSL to symplectic Euler. Let's say we leave everything the same and run it. I may have to kill it at some point. It actually bombs out, but we can make it actually work. However, you have to change a few things. So if we go here to scenario parameters, let me change this thing. Let me just change this thing to, I don't know, maybe 2 and make this thing even smaller. Okay. Make this thing same. Just give it a minute. Let's run it. I should have deleted that path there. I forgot to do that, but it's okay. It bombs out again. However, you can see it's going around the circle, but it's not the circle that we want. So let me go ahead and do one more thing. Let me go there and change this thing to, I'll put another 0 here. And now run it. This is symplectic Euler. Okay, what it's saying is that this geometric set, let me go and delete this. Let me go here, delete that. It's complaining because it couldn't do the spline in the path, so I'm going to delete that. All right, delete it. Let's go back to our dynamic scenario and run it now. Okay, this may take a couple of minutes. That's all right. You get to see this disk is spinning, but it's not precessing. At some point, it starts to precess, and all the numbers are way off. I mean, if you look at the stuff, the order of basically it diverges to infinity, but the path almost is a circle. No, not really. We'll see. Let's give it a minute. So the moral story is that I could not model this thing into the experience with dynamic scenario. It's not quite clear what I'm doing wrong. I hope that the people at the SAW will be able to address this, but I don't know. See, just give it a minute. Gradually, it will go around, but not at the circle that we expect. It's going to be a circle, but at a tilted angle. And the numbers are way off as far as the velocity, as far as the angular velocity, etc. It's all pretty much garbage. Just give it time. I think it's educational to see what's happening here. It's still not precessing. Still not precessing. But it will. It's definitely going through some kind of unstable motion, but just give it time. In a few seconds, it starts to precess. You can already see that it's doing it. It's not standing where it was. Do you see that? Definitely it's not along that plane that we are there. You see? It's going around some kind of a path, which is kind of a circle with some notation, but not where I expected it. If I rotate this, I can actually align it better with that circle. Moving this thing around so that I can perhaps line it up. Look at it from the top. Yeah, there. This is the correct view. This is supposed to be taking place in the XY plane, and it's not. I'm not going to stop the job. I want this thing to finish because I also want to show you the the points, the trace. There's going to be 20,000 points. So because I asked for the result every 0.001 second, 2,000, 20,000, yeah. You can see that it's almost around the circular path. Almost there. There's so many points that even you will not be able to put the spline on it. It will show us the points associated with the trace of that point that I pick, that I will pick, but the spline you won't be able to do it because it's probably so computationally expensive. Going through 20,000 points is just meaningless and useless actually. We're almost there. Because I want to show you something else that I've already done in other videos, but I want to remind you, refresh your memory on how you do this thing that I'm going to do. It's almost finished. Now remember, this is all on the cloud. That's why later on when I try to do a little bit of post-processing, it's very sluggish. Believe me, it's going to be the same story if you do the 40-degree angle. I've tried it and same kind of behavior, very bizarre behavior. Eventually, it will go in the precession as it's supposed to, but the numbers are completely out of whack. Okay, almost done. Yep, it finished, but this post-processing, getting the post-processing data is going to take a few seconds. Almost. I'm sure if you're bored, you'll probably forward this thing to the end of the video and see what I'm going to be doing next. I have to wait here and sit for this thing to finish because I want to show you something. This is real time. I'm not fast forwarding it. Real time. Okay. Scenario simulation is completed. As you can see, the message on the top right corner says, okay, done. Now, just give it a minute. Still thinking. Okay, very good. You see this? You see the viewing results right now. You click on the play animation. What I can do, I can drag the sliding bar and move it to the right, maybe kind of almost to the end, and then we can play the rest of it. Okay. So initially, of course, if I looked at initially, it goes crazy like this. Remember, it was spinning, but it was not precessing. So eventually, at some point, it will start the precession process. Yeah. The other thing I want to show you is if you click on this geometric trace and you select that point, oh, not that, cancel. I wanted that point. Let me turn it around, select this point. Say, okay, look, there's 20,000 points here. Then you can still copy and paste it, but the spline is not going to be created because it's 20,000 points. But I want to show you what that cloud of points look like. Now I could have used, for example, results not every 0.0001 second. I could have done it at every 0.01 second, but that's you can play with that. It's going to be faster, but I wanted to show you here that the path is actually circular, but not the circle that we expect in the XY plane. Still thinking? It's almost done. There's this message there again on the top, which has to do with display of the results. So this is going to go into another shape. There we are. See this? Now what I can do is I can go here. Notice that there's an exclamation mark here because if you scroll all the way down, there's no spline. Spline is not generated. So right click copy We can do a copy. We go to our model here into the assembly and paste it. Paste it. There. Okay, that's what it was worth the wait. And you can actually go to the results. See, this is the path that it's processing about, and it's not in the XY plane. So if you go to the results here, again, if you go to the play animation, scroll this thing to a place that you want. See, eventually, right there, you see, it's going around that path. Let me play it from here. We can slow it down, by the way. See this? It's going along that path, along that circular thing. This thing so that you can see it better. Right there. But it's also going up and down. There's notation involved there too. All right, folks. So I miserably failed in modeling this problem, I guess.